All right, y'all. So this is the chemistry HL paper 1AB and paper 2 all in one. So we're just going to go right into this, starting with number 1 of paper 1A. What is the concentration of chloride ions in mole per decimeter cubed in a solution formed by mixing 200 centimeters cubed of 1 mole per decimeter cubed hydrochloric acid with 200 centimeters cubed of 5 mole per decimeter cubed of sodium chloride? So to do this, we have to find out first the total moles of chloride ions divided by the total volume. Now, both of our things, sodium chloride and hydrochloric acid, will provide us with 1 mole, so we can just use their molarity values. So we're going to go ahead and take 0.2 decimeters cubed of our HCl, because you'll notice all I did was just convert that into a decimeter cubed. And I'm going to multiply that by 1, and I'm going to add it to 0.2 and multiply that by 5. So what I'm doing is I'm taking my volume and my molarity and multiplying them together, and I will get moles. And then I take my volume and my molarity and multiply them together and get moles. And I'm adding those two values up right here. When I do that, I will get 1.2 moles of chloride ions in a total volume of 0.4 decimeters cubed, because now my volume is 200 plus 200, or 0.2 plus 0.2. That gives me a total molarity of 3. All right. Number 2, 0.02 moles of zinc is added to 10 centimeters cubed of 1.0 molar hydrochloric acid. How many moles of hydrogen are produced? Well, to do this, we have to find out first which is the limiting and which is the excess reagent here. So I can find that if I have 0.2 moles of zinc, I need to see how many moles of hydrochloric acid I have, so I can compare my molar values. If I take 0.01 decimeters cubed, which is again just our 10 centimeters cubed, I'm going to be doing those conversions a lot, and I multiply it by 1 mole per decimeter cubed, our molarity, I get 0.01 mole HCl. So I notice here that when I have 0.2 and 0.1 mole, I can convert them both into hydrogen. 0.2 moles, because it's a 1-to-1 ratio, will create 0.02 mole hydrogen. Meanwhile, this is a 2-to-1 ratio, so 0.1 divided by 2 will get me 0.005 mole hydrogen. Now, when I compare these two values, I notice that I get less here. Therefore, hydrochloric acid is my limiting, and therefore my answer is going to be A, 0.005 moles. Ooh, my graphs did not work here in the transfer. Maybe they are elsewhere. Well, let me just go ahead and rewrite the actual graphs. I kind of have my moles in the middle of this one. All right. So what is the relationship between moles and our temperature? Well, in PV equals nRT, we notice that moles and temperature are on the same side. So if we were to just reorient, we can say N is equal to PV over RT, and we're assuming that PV and R are all going to stay constant. Therefore, N is equal to 1 over T. So this is going to just be an inverse graph. And so, oh, I have to draw in my answer options. All right. I believe these were the answer choices here. If we look at the value of n equals 1 over t, clearly our answer is going to be B. Answer is B. All right, moving on to number 4. What is the relative atomic mass of an element with the following mass spectrum? Well, 80% or 0.8 has a mass of 23, and 0.2 or 20% has a mass of 28. So we can just take our percent times our mass, and we add it to our other percent times our other mass, and we find that our mass is 24. Another good way to look at this is about 80% or 4 out of 5 this one, and 1 out of 5 this one. That means it's going to be closer. If we divide this into 1, 2, 3, 4, 5 equal sections, it's going to be the one furthest away or closest to the one that has a larger amount. But honestly, we can just use the formula of percent times mass plus percent times mass, etc., for however many percentages you have. All right, what is the correct order for increasing first ionization energy? So when we look at sodium, magnesium, and aluminum in our periodic table, they're all in period three, and this is in group 1, group 2, group 13, and furthermore, this is our S block and this is our P block. If we then look at the energy levels of these, this is our 3S and our 3P, so this is energy. And we look at the ionization energy, which has to do with the outermost electron. When we look at the 2 electrons that would fill sodium, so I'll actually use a different color for each. We'll say black represents outer for sodium, blue represents outer for magnesium, and purple represents outer for aluminum. So purple, blue, and black. We have to pay careful attention to where they are. So we notice that the 3s electrons are actually in the same place. So to determine which has a higher energy level or which has a higher ionization energy, it's not so much about how far they are from the nucleus. It's not so much about their energy. It's instead figured out via the fact that we have 12 protons in magnesium and 11 protons in sodium. And because we have more protons in magnesium, it's going to be harder to remove that outer electron. It has a stronger effective nuclear charge. So we definitely know that magnesium is going to be greater than sodium. So anywhere where we see magnesium greater than sodium, that's cool. So it can't be this one because magnesium is less than sodium. Furthermore, we have aluminum. Aluminum has 13 protons. I'll write that actually up here, 13 protons. And we know the general trend for the periodic table is as we move across right, the ionization energy increases. And again, that's due to the Z effective or effective nuclear charge. So we also know aluminum should be greater than sodium. So anywhere where aluminum is less than sodium, that can't be true. So D is wrong. So now we have to figure out which of these is correct. Which one has more, aluminum or magnesium? And this is that weird case where this trend does not perfectly follow. Because aluminum's all the way here in the P block, it actually is further away from the nucleus, which would be represented down here. And because it's further away, it is easier to remove those electrons. When we move from the S to the P level, we actually find that there's a slight increase or decrease in ionization energy. So our trend is sodium, aluminum, magnesium. All right, moving on to number 6. Which are the most reactive elements of the alkali metals and the halogens? All right. Well, again, this is just kind of periodic trends. So if I just draw my periodic table, we generally have this trend where up and to the right, we have more reactive, active nonmetals. And down and to the left, we have more reactive metals. So basically, we're just looking for the furthest one up here and the furthest one down here. We don't really talk about francium. So with that out of the pocket, we just are left with cesium and fluorine. Moving on, number 7. 8.8 grams of an oxide of nitrogen contains 3.2 grams of oxygen. What is the empirical formula of the compound? Well, there's a couple ways to do this, but the easiest way is to just calculate how many moles of each are in this compound. So if we have 3.2 grams of oxygen, we can convert that to moles by taking 16.0 grams is 1 mole. And here we're talking about atomic oxygen, just O, because the whole thing is oxygen. If we said O2, we would have to say 32, but that makes it a little harder for empirical formula, so I'm not. So what we get here is we find that 3.2 divided by 16 is about Oh, sorry, 3.2 divided by 16 is about 2. Sorry, zero point 0.2. All right, so now we just have to figure out how much is going to be nitrogen. So if 3.2 of 8.8 is oxygen, that must mean that 5.6 grams is nitrogen. Now 5.6 divided by 14.01 grams is 1 mole of nitrogen. And once again, we're still just talking about elemental nitrogen. That is going to equal to zero point 0.4. So it's 0.2 mole oxygen, 0.4 mole nitrogen. We divide by the lowest amount, zero point 0.2, zero point 0.2, and that gives us 1 oxygen to every 2 nitrogen. So it's B, N2O. All right, moving to number 8. Number 8 tells us a couple things, and we get this nice color wheel with us. We see that chromium hydroxide is, or sorry, chromium hexahydroxide, or sorry, chromium hexahydroxide is violet, and chromium hexa ammonia is yellow. What is correct? Well, we notice that if this is violet, following the color wheel, if the color is violet, then we are absorbing yellow. Absorbing yellow. If the color is yellow, we are absorbing violet. Absorbing violet. All right, so the wavelength of light absorbed by CrOH2 6 3 plus should be the yellow one, 5.8 times 10 to the 7th. So our answer has to be either A or B. D-level splitting caused by H2O compared to NH3 ligands. So what this is saying is that in the d orbitals, when they split into our d orbitals, the distance is that greater with H2O or greater with NH3. The distance actually tells us what energy is going to be absorbed. A greater distance means larger energy light, larger energy light. And we know that light energy is inversely related to wavelength. And also, if you remember your electromagnetic spectrum, violet is higher energy. So we know that to absorb violet equals high energy, which would therefore equal more splitting. So H2O absorbs yellow, meaning it absorbs lower energy, meaning it has less splitting. So the D-level splitting of H2O has to be less than ammonia, B. All right, number 9. Which of the following compounds does ionic bonding predominate? Well, HCl is going to be both covalent. NAF is ionic. NH4Br is actually both ionic and covalent. And the same for NaOH. So predominate tells us that something is only going to be ionic, B. What is the main interaction between liquid CH4 molecules? CH4 is a symmetrical molecule with no net dipole moment. And because it is symmetrical, 2 M's, we have nonpolar, no dipole. We cannot have dipole-dipole. We cannot have hydrogen bonding. So it's either London dispersion or covalent, but this is a liquid. We're talking about the forces between molecules of a liquid. That has to be an intermolecular force. Therefore, it must be A, London dispersion forces. What is the formal charge of the oxygen atom in hydronium? So we have to remember that there's a formula for formal charge, which is formal charge is equal to the number of valence electrons minus the lone pairs of electrons, or sorry, not lone pairs of electrons, just lone pair electrons. So specifically, how many electrons are in lone pairs, minus 1/2 the number of bonded electrons, which means we have to draw this thing out. Now, hydronium just looks like water with this one exception. You add another hydrogen, replacing one of the lone pairs, and you put some brackets and a plus. So to calculate this out, our number of valence electrons around oxygen is 6. Oxygen still has 6 valence electrons naturally. This means this we're talking about naturally, not in this scenario. But it naturally has 6. The number of lone pair electrons is 1, 2. The number 1/2 are bond electrons, 2, 4, 6 electrons. So this is equal to 6 minus 2 minus 3, which is equal to 1. Formal charge is positive 1. All right. What is the molecular geometry of SF4? This requires our expanded octets, our expanded molecular geometry. So sulfur tetrafluoride has this weird thing where we still have sulfur, which has 1, 2, 3, 4, 5, 6 valence electrons, and each fluorine, and sorry, I'm going to abbreviate my electrons. Whoops. Each one of these fluorines only wants to form one bond. And what ends up happening here is we actually get this weird expanded octet where we have these two normal bonds, but we also have two more bonds that sneak in there. And we get our 2 on the top and bottom, but we also get this weird shape here. And now we have 6 sets and 4 bonds. What I see here is a square shape. It is actually square planar. We have our lone pairs creating a repulsive force there on the top and bottom, and this gets us D, square planar. All right, moving on to number 13. The graph shows the first 6 ionization energies of an element. In which group is this element? So we notice the first ionization energy is pretty low. Second one is higher, but no real big difference. Third one's even higher, but no big difference. To ionize that fourth one, we jump incredibly far. There is a massive change. Same with the fifth and sixth. So what we're looking at is an element that's okay to lose 1, it's okay to lose 2, it's okay to lose 3. So probably something that forms a 3 plus charge. So generally something in group 13, like maybe aluminum even might be a very possible version of this element. Losing those extra ones takes such a large increase in energy, it's unfathomable. Now, you may also say, well, why not something in group 16? Something that has 6 valence electrons, something like maybe oxygen. Because when we look at oxygen, what we're going to see, if we look at the 2p orbital on oxygen, removing, 1, 2, 3, 4, 5, 6, removing the first one, then the second one, then the third one, that one from the first level will steadily increase, finally having a much larger increase on the fourth, fifth, and sixth one. However, we still have the 2p range, which wouldn't create such a drastic jump. So we would actually see another big jump from 5 to 6, and we're not seeing that. So with that said, it's probably 13. Number 14. Which equation represents hydration enthalpy? Hydration enthalpy is just taking something from its solid to its aqueous state. So really, it's just C. We're hydrating it. We're dissolving into water. All right. 15. What are the signs of delta H and delta S for the reaction that is non-spontaneous at low temperatures, but spontaneous at high temperatures? So generally what I like to do is write our equation. Delta G equals delta H minus T delta S. If it is non-spontaneous at low temperatures, what I just try and do is imagine the lowest possible temperature, which might be 0. So what I'm trying to do is find out how do I make delta G positive when I only have delta H, because we're going to imagine that T is just 0 and therefore canceling out our delta S. Well, if I want it non-spontaneous at low temperatures, delta H should be positive. So it's either going to be C or D. But I want it spontaneous at high temperatures. Okay, so I'm going to throw a negative sign as G. And now because T is so high, I'm going to say delta H minus infinity delta S. And if I see that T is going to be infinity, it really doesn't matter what H is. So how do I make delta S times infinity still negative? Well, in that case, delta S must also be positive, because if it was negative, that would therefore cancel out the negative in front. So it has to be D. All right, number 16. Which equation represents the bond enthalpy for HBr and hydrogen bromide? Well, bond enthalpy is literally defined as the energy in the bond between two gaseous molecules, through the formation of two gaseous molecules, or two gaseous atoms. So what we're doing is we're breaking a gas version of this into a gas and a gas. These are just definitions here. So it's going to be B. Which term in the expression delta G is equal to delta H minus T delta S is an indirect measure of the change of the surroundings when divided by T? So generally what I want to do here is I just want to see what each of them is divided by T. So what I'm going to do is take my equation delta G equals delta H minus T delta S. From this point, we realize that we have to be looking at delta S. Delta S, we actually get our delta S surroundings. Surroundings. We have to understand that that is equal to negative H divided by T. And from here, we can see that if we take our H and divide it by our temperature, that just ends up getting our entropy of our surroundings. Therefore, it should be B. So number 18, why does a reaction for a sample of gases at constant temperature occur faster at higher pressure? So this is just collisions are more frequent. Remember that pressure is just force over area, and when you squeeze these together, they're going to be applying a much bigger force because they're colliding more with the surroundings around them. And because we have more collisions, we're going to be having more opportunities for a reaction, and more opportunities for a reaction is a faster reaction. All right. So number 19, which compound are all carbon atoms sp3 hybridized? So when we're looking for sp3, what we're really just looking for is carbon to have 1, 2, 3, 4 bonds. So in C2H2, the only way we can get that is having 2 bonds. These are just sp hybridized. C2H2Cl is still a double bond. There's a lot of ways to draw this. Cl, Cl. But again, this is sp2 hybridized. C2Cl4 is kind of the exact same thing, but C2Cl6, that is 3 chlorines on each. So this is going to be D. All right. Number 20, the equilibrium constant Kc for reaction 2A plus 4B reacts to produce 2C plus 4D has a value of 4. What is the value of Kc for the reaction below at the same temperature? So what I'm actually going to first do is write the Kc for the first reaction. And the Kc for the first reaction looks a little bit like this. C squared plus, or sorry, not C squared plus C squared D to the fourth divided by the concentration of B to the fourth concentration of A squared. And when I do that, I say that's equal to 4 because that's our Kc. It says so right there. So what I'm going to try and do is get my K equation, my equilibrium constant equation, to match what it should look like for that. So what do I mean? Well, I want it to be A times B squared is equal to, or over C times D squared. So what can I do to make these things the same? Well, the first is I notice all my exponents are honestly way too high. So I'm going to square root both sides. When I square root both sides, I get C D squared divided by, and I'm going to switch these around from how I said it before, A B squared is equal to 2. This is almost exactly what I want, but the problem is I need to swap those. So what I instead do is I multiply both sides by the negative first power. I take the inverse. So that's going to get me A on the top, B squared, over C on the bottom, D squared. And that's going to get me 1 over 2, which is 0.5. And there it is. This whole thing is honestly just which algebraic operations can I use to achieve what I want. And that's it. 21. zero point 0.5 moles of I2 and zero point 0.5 moles of Br2 are placed in a closed flask. The following equilibrium is established. Ooh, whoops, my little arrow did not go through. Oh, this is equilibrium. I should just do the equilibrium arrow. The equilibrium mixture contains zero point 0.8 moles of IBr. What is the value of Kc? Well, you might want to do an ice table, and that could work, but truthfully, we don't need to. What I'm first going to do is write my equilibrium constant, which is just IBr squared over iodine times bromine concentration. So you're saying, well, what's the values? Well, the reason we don't need to is because we have conservation of mass and conservation of matter. If we have 0.5 moles of two gases, that means we have a total of 1 mole of gases. We notice that for 0.5 mole of each of those, they end up going to 2 moles of that if it completed all the way, but it doesn't. But we have 1 mole of gas. Now we end up with, oh, sorry, 0.8 mole of IBr, which means we should have 0.1 mole left of each. And so it becomes 0.8 squared divided by 0.1, 0.1, and therefore our equation must be zero point 0.8 squared over 0.1, 0.1. That is equal to 64. That is our equilibrium Kc. All right, 22. What happens to the amount of hydroxide ions and hydroxide ion concentration when water is added to a solution of NH3? So for this, we need to be able to infer that NH3 plus H2O creates an equilibrium in which we get NH4 plus OH minus, because NH3 is a weak base. So if we add water, Le Chatelier says we're going to force the equilibrium that way, and we're going to produce more OH. So the hydroxide ion concentration should increase. Or sorry, the amount of hydroxide ions should increase. But one of the other things is we have to look at the hydroxide ion concentration. Because this is a weak base, our equilibrium, our Kb, is less than 1, meaning that as we add more water and shove the equilibrium this way, we're still adding a lot more water than amount of hydroxide we're getting out. We're still diluting it. And because we're diluting it, the actual concentration is decreasing. All right, moving on, 23. What is the strongest acid in the equation below? Well, Kc is less than 1. Because Kc is less than 1, we know the reaction tends to move that way. So now we just have to look at these two. Which of these two is an acid? And H3O plus hydronium we know is going to donate that proton. This is a Bronsted-Lowry acid. Therefore, it's H3O plus. Number 24. Oh gosh, all my curves are just absolutely getting destroyed here. So I'll redraw this. It looks like we have something like this. Oh, it is actually important that I get this curve just right. So with this curve here, our question asks, a weak base is titrated with a strong acid. Which value of pKb can be estimated from the titration curve? Well, that's a funny thing. At our half equivalence, pH equals pKb. It's one of those little things that you have to know. So our equivalence point happens right around 50. Therefore, our half equivalence at 25 happens right just above 9. Therefore, our pKb must be 9.2, right at the half equivalence point. 25. Which species are both both Lewis and Bronsted-Lowry bases? So when looking at this, the first part is the Bronsted-Lowry base. That one's pretty easy. Anything that accepts a proton. Protons. So they all accept protons. We know ammonia does to become ammonium, hydroxide does to become water, and cyanide become hydrogen cyanide. So for that, I mean, these ones are just easy. They have the electrons on them anyways. We know that 1, 2, and 3 all accept protons. Oh, 1, 2, and 3. Typo. But what about Lewis bases? Well, Lewis bases donate electron pairs, basically meaning that they have an electron pair for something to bond to. If we look at cyanide, it looks like this. We've got electron pairs up the wazoo. If we look at hydroxide, it looks like this. Electron pairs. If we look at ammonia, it looks like this. All of these can act as Lewis bases. So our answer is D, 1, 2, and 3. All right, moving on to 26. Ice containing only the isotope H2 sinks and does not melt when dropped in ordinary distilled water at 3 degrees Celsius, which is correct. The isotope hydrogen 2 has high natural abundance. Honestly, where does this get stated? It doesn't. So maybe it's true, maybe it's not. We have no way of knowing from the question. It honestly has nothing to do with it. The H2O solid, so the ice made with H2, has a higher melting point. Well, maybe it might, but from what we gather, we're at water at 3 degrees Celsius and it's still ice. It's solid. It is sinking. They didn't say it's melting. So we have nothing really to go off to answer B. H2O solid has a lower density than normal ice-cold water. Well, it does sink, implying a lower density. That sounds pretty good. I think I'm going to go with that one. H2O from hydrogen 2 has different chemical properties. Well, we have nothing to signify a chemical reaction. We have no bubbles, gas production, no color change, no precipitate, nothing. There is no chemical reaction. We have nothing that tells us. So it's got to be C. All right, 27. Why is copper 2 sulfate blue? Red light is absorbed when electrons are promoted between the orbitals in the split d sublevels. I mean, honestly, that already sounds good. We actually did a problem way before. So if we look back in our test, maybe too far? Nope, not far enough. Let's see. Red is kind of opposite blue. Maybe it should be greenish. Who knows? But Absorbing red probably gives us something in this color range. So going back, sounds pretty good. I think I'll keep an eye on this one because it sounds like an answer. That is kind of why things end up being blue. Blue light is emitted when electrons fall between orbitals. Well, for blue light to be emitted, we have to have electrons that are excited, which means we have to put energy into the solution. And copper sulfate is just blue regardless of our input of energy, so that doesn't really make sense. Red light is absorbed when electrons fall between orbitals. We know that the falling of orbitals emits energy, so that just can't be right. Blue light is emitted when electrons are promoted. Again, we can't have the emission unless we already have the promotion. And also, electrons are not emitted when, sorry, light is not emitted when electrons are promoted. That doesn't make sense. It's only when they fall. So it's got to be A. 28. The potential energy profile for a coffee cup calorimetry experiment is shown below. We notice a couple things. We go from high energy to low energy. What is the correct interpretation of this reaction? Well, if we're going from high energy to low energy, that means it's releasing heat, releasing energy. That's going to be exothermic. So it's either A or C. And if it's releasing heat, that thermometer is going to absorb that, and we're going to record an increase in temperature. A. All right. That one wasn't too bad. Moving on to 29. The diagram shows the energy profile of a reaction. What combination is correct? So activation energy of the forward reaction. Well, forward reaction activation energy is this. Therefore, it's going to be our y minus our x. So either B or D. Our activation energy of the reverse reaction. All right, so it's going to be this. It's got to be this time our y minus our z. All right, answer is B. All right, number 30. A sample of calcium carbonate reacts with excess hydrochloric acid in a beaker. That excess is going to be important. The solid line shows how the mass of the beaker changes with time. Which dashed line represents results obtained when the acid concentration is doubled? Well, it's already in excess, so we're not going to have more product, meaning we're not going to have a changing endpoint. The only thing is when we increase the concentration, we are going to increase the rate. We have put more things in that do the reaction. So we're still going to get the same endpoint. We're just going to do it faster. That's a B. All right, so that was paper 1. Moving on to paper 1B. A student investigates the effects of the exposure to air on the ascorbic acid, vitamin C concentration in specific orange juice. Equal volumes of orange juice are sealed, identical flasks, placed in a refrigerator for 2 weeks. The samples are in the refrigerator are exposed to the air by removing the stopper for a different number of hours each day. Identify 2 variables that are controlled. There are so many. The type of flask, the type of OJ, the temperature, the time in fridge, the type of stopper, the amount of juice, of juice. Pretty much anything that isn't changed is a control variable, which is almost everything. All right. The concentration of ascorbic acid is determined by titration with standard iodine solution. Every few days, 10 centimeters cubed of orange juice is removed from each sample, diluted to 100 degrees diluted to 100 centimeters cubed and titrated. Suggest why dilution before titration. So one of the key aspects of dilution is that if we have smaller concentrations, we can identify changes better. We can identify changes better. Just another aspect of this is we're looking for a color change when we use iodine. And if we're looking for a color change with iodine, we want something that's clear and less cloudy. So it helps with visibility. visibility of reaction. All right, identify a possible systematic error with this method regarding the sample that is exposed for 0 hours. Well, there is already air in the flask. So already from the start, we're talking about ascorbic acid that has some connection to air, some part that is already likely going to be oxidized in some way, shape, or form. So we can't fully remove the exposure from the air. Suggests how an additional flask could be set up to verify where the air has occurred. You could like remove juice with a syringe and fill the flask so there is no air. Remove the air in some way, shape, or form. The following data is collected during a titration. Calculate the percentage uncertainty of the titrate. So for this, we have to notice a couple things. What is the total amount that is actually being used? So to find the total amount, we're going to take 16.1, whoops, 16.1, and we're going to subtract 1.10, and we get a total amount of 15.00 centimeters cubed used. Now we have to find the uncertainty. If we have plus or minus 0.05, that really means we have a total change of 0.1 because we could be up 0.05 or down 0.05, but that whole difference is 0.1. So we have 0.1 divided by 15.0, and we get 0.0067, repeating. So what we're going to do is multiply by 100 to get a percentage, and we get 0.67%. All right, the following graph shows students' results. Calculate the average rate of decrease of ascorbic acid concentration for the 24-hour sample over the period of 14 days. So we're only looking at the 24-hour sample. So what we're going to do is we're just going to take our start point and our end point. That's what we're going to focus on right here. So for this, we're just going to take our total change, and we want to set our amount over time. So we're going to do our y minus our x. So 1.1 minus 5.3. This is my 1.1. This is my 5.3. Just kind of like finding slope, basically. And 14 minus 0. That's going to be negative 4.2 over 14, which, to be fair, they're asking for the average rate of decrease. So I'm just going to remove this minus sign because we already know it's a negative because we're saying rate of decrease. So 4.2 over 14 is 0.30. Now, that is not fully correct. First off, we know that it is times 10 to the negative third moles per decimeter. So we have to add that back, times 10 to the negative third mole decimeter cubed, and that is divided by our time unit, which is day. So you needed to have your units, your scientific notation, all correct to get the full points. The student's hypothesis is a lower ascorbic acid concentration will be found in the juice exposed to the air for longer due to oxidation of ascorbic acid by oxygen. Discuss whether the data supports the hypothesis. So one, you have to say, yes, it does. Two, you have to reference the data. All trials showed a decrease in concentration. However, the largest decrease was in the 24-hour exposure, followed by each subsequent quint. amount of exposure time. Basically, you have to say that they're correct because it decreases, but especially because the longer it was exposed, the less ascorbic acid was found in the solution. You have to be very clear about that. All right, moving to 3. State the implications and results of the experiment for avoiding loss of vitamin C. Don't expose it to air. Don't expose to air. Very clearly, that's what we need to say. Something about don't expose it to air. Storage should be good. Suggest an extension for the investigation. Pretty much anything that you can do where you would talk about maybe longer exposure, or one of the biggest ones is try different temperatures, different temps. See how that changes the rate at which it oxidizes. All right, moving to number 2 on the IHL test. So this one, oh, it got cut off. A student investigates the effect of pressure on the volume of carbon dioxide gas released from a carbonated drink poured into a flask. To alter the pressure on the carbonated drink, masses are placed on top of the piston on the gas syringe as shown below. The graph shows some of the data collected. A, determined by annotating the graph the initial rate of release of CO2 in the experiment 1 in centimeters cubed per second. So they just want the units that are here on the graph. So to find initial rate, what you need to do is first set up a tangent line. Now, the IB is very good about making sure that you do not use the first 2 points. Whatever you do not use the first 2 points. They will be looking for that. You take time 0 and draw an estimated tangent line. From there, I just try and find an intercept that looks nice. To me, that one looks nice because then I can use right here. I'm going to use 20 and whatever that time is. So this should be 20 and 15 seconds. And then I'm just, with that annotation right here and these 2 points as shown, I'm going to just go ahead and figure out that I'm at about 20 minus 0 over 15 minus 0. And when you calculate that out, you get a 1.33 repeating. So I'm just saying 1.3 centimeters cubed. Second inverse. Make sure you use the units that they provided to you. Now, I believe on this one, they accepted a pretty big range of like 1 all the way to like 1.6 or something like that. But make sure that you have a clearly drawn tangent line that you're following and you have the 2 points illustrated that you're using for your tangent. Another good one just for this trial is there's a nice intercept right here at about 7 and 5. Find something that's pretty easy to use based on the data they give you. Estimate the time at which the piston would begin to move if a 600 gram mass is used. Well, I noticed an increase of about 10, then maybe 15. So I'm just going to chalk it up to 20, assuming a bigger increase. So I'm going to say maybe 45 seconds. Again, the IB is pretty lenient about this. Their range is, for this one in particular, was 40 to 60 seconds. So anywhere in that range is good. Suggest 2 reasons why the volume of CO2 collected in the gas syringe is smaller when more masses are placed on top. So you could say at high pressure, gas takes less volume. So I guess pressure increases, volume decreases. The other one is that at high pressure, more gas is dissolved in the liquid. That's kind of why when you open a soda can, you hear that sound because gas is being released because the pressure is decreasing as the pressure in the can equilibrates with the pressure of the outside air. And so we have that decrease in pressure, and gas that was previously dissolved is no longer dissolved. All right, paper two, finally. A monoprotic acid, HX, is found to have the following composition by mass. Determine the empirical formula. All right, so for this one, we're going to take 39.99 grams carbon. We'll divide it by 12.01. So I'm just going to assume these are gram values because that's how you do empirical. Assume 100 grams. And you get a mass of 3.33 mole carbon. For the next one, 6.73 gram hydrogen divided by 1.01, and you get 6.66 mole hydrogen. Lastly, oxygen, 53.28 gram oxygen divided by 16.01, or sorry, 16.00, and you get, again, 3.33 mole oxygen. So when you see this, you can divide by the lowest amount, which was 3.33, 3.33, and 3.33. And we find that we have two H's, one carbon, one oxygen. But we have to be careful. They ask for the monoprotic acid HX, so we have to put a hydrogen in front. That's one of our hydrogens. They also say it's monoprotic, so it's not H2. It is H. Therefore, it's HCHO. HCHO. So we have to be careful that we are doing this correctly according to what has been given. Monoprotic HX acid. All right. B, 25 centimeters cubed of a solution containing 1.51 grams of HX is titrated with a 0.750 mole per decimeter cubed solution of NaOH aqueous. The HS solution is exactly neutralized by 22.30 centimeters cubed of the NaOH solution. Determine the molar mass of HX. So there's so many things to do here, but the first thing is just figure out what you actually have. What they have given us is a volume and a molarity of NaOH. So we're going to start with that and see where it goes. From my volume and molarity, I have 0.750 times my volume of 0.02230, and I get 0.0167 mole NaOH used. Cool. So I know how much mole of NaOH was used. Now, they do mention that this is a monoprotic acid, HX. So if I think of other monoprotic acids like HCl, and I add that to NaOH, generally monoprotic acids go pretty well in making a 1:1:1:1 ratio, as we can see in this reaction that I'm going to draw a little clear, NaCl. Monoprotics with a base like NaOH are pretty much always a 1:1 coefficient. Awesome. So if I have that many moles of NaOH used, turns out that's how many moles, 0.0167 mole of our monoprotic acid, HX, we have consumed. All right, we have a mole volume, or sorry, we have a mole amount. We have a mass. If we have a mole and a mass, we can get a gram per mole, which turns out is the molar mass units. So to get grams per mole, we take our grams, 1.51 grams HX. We divide it by our moles, 0.0167 mole HX, and we get a molar mass of 90.42 grams per mole HX. There we go. This is one of those things where all you really need to do is use dimensional analysis as well as what you see in the equation. What I did in this first aspect was also dimensional analysis. This was my volume decimeter, or sorry, this was my molarity, mole decimeter -3. This is my volume, decimeter -3. When I multiplied those together, I got moles, which I equated to moles again, which I then divided by our grams to get a molar mass. It was pretty much all dimensional analysis. C, state the molecular formula of HX. Okay, well, to find the molecular formula, I have to find out how much HCHO weighs. When I do that, I notice that's 1 plus 12 plus 1 plus 16. About. It's about 30 grams per mole. And I'm trying to get to 90.42 from the one above. Therefore, if I multiply it by 3, I will get about 90 grams per mole. So I know that my molecular formula should be HC3H2O3. Remember, this 2 plus our 1 still is 3, but we have to make sure that we have an H in front because, as we know, it's a monoprotic acid, HX. All right, that was that problem. Moving on to number 2 of this group. Hydrochloric acid is an important chemical reactant in industrial chemical. A pH probe is placed in a small volume of 0.1 mole per decimeter cube solution of hydrochloric acid. The pH is recorded while steady stream of distilled water is added to the acid at a constant temperature. On the axis, sketch the graph of pH against volume of water added. Well, initially we know our concentration is 0.1 mole per decimeter cubed. So if I take my pH equals negative log 0.10, I find that my initial pH should be 1. So your graph should start at 1. Next, we're adding water. So we are going to be diluting it. So that means we're going to be getting some graph that's going up. But the question is, where do we end? Well, we're starting with acid. We're not adding base, and we still, when we're done, have an acid. So no matter what, because we're starting with acid, we should always make sure we remain below 7, because no matter what, this is still going to be acidic. It should be a nice curve that levels out. So when you're doing this, please make sure to be careful. You are still going to keep it acidic, so it should still be below 7. 7 is your hard line for neutral, but we are starting with an acid. So once again, we're keeping it below 7. All right, moving to number 2. The experiment is repeated using 0.01 mole decimeter cubed of sodium hydroxide at the same temperature. State the initial pH of the sodium hydroxide solution. Well, we can use a very similar equation. pOH is equal to negative log of 0.010, which gives us a pOH of 2. If we take pH is equal to 14 minus pOH, we get pH equals 12. So our pH is 12. And that sounds right because it's basic, and sodium hydroxide is basic. All right, moving on to number 3 of paper 2. Heptadecane can be broken down into smaller molecules. Consider this reaction. Determine the standard enthalpy change, delta H, for the reaction stated using section 12 of the data booklet. Section 12 is bond enthalpy, which means we need to find bonds, which means we kind of have to draw these out. C17H36 is just a bunch of single bonds. Each hydrogen is bonded to one carbon. So if we have 36 hydrogens, we're going to have 36 hydrogens bonded to carbons. Furthermore, taking this example up here, if I have 1, 2, 3, 4 carbons, I have 1, 2, 3 bonds. So if I have 17 carbons, I should have 16 carbon-carbon bonds. Next, for our other products, C2H4, there's only one way to draw that. And for C13, H28, we're going to follow the exact same pattern we did with heptadecane, C17, H36. That's going to be 28 hydrogen carbon bonds, and that's going to be 12 carbon bonds. All right. So to determine the standard enthalpy change for the reaction using section 12. So we have to know that when we're using bond enthalpy, we're using the equation bonds broken minus bonds formed. So before I even put values in, I'm going to try and keep track of how many bonds are broken, how many bonds are formed. So I find from this, I get, sorry, I'm just double checking my work here. I find from this that I have, for my bonds broken, 36 hydrogen carbon bonds. I also have 16 carbon carbon bonds. These are my bonds broken. Then I have my bonds formed minus. I have 1, 2, 3, 4 plus the 28 I already have here. 32 hydrogen carbon bonds. I have 12 carbon carbon bonds. Carbon carbon bonds. I have 1 carbon double bond carbon bond. These are my bonds formed. To make my life easier, I'm going to cancel out some of these. All 12 carbon-carbon bonds are balanced by almost all 16. We're going to have 4 remaining. 32 of my hydrogen carbon bonds are going to be balanced by almost all of these, so I'm going to have 4 of those remaining. My 1 carbon-carbon double bond will stay the same. So what I end up with is 4 times my hydrogen carbon bond. So I'm going to write this a little cleaner. 4 times my hydrogen carbon bond plus 4 times my carbon carbon bond minus my carbon carbon double bond. So this is how I'm going to solve this problem right here. Before I go further, I realize I did make one little mistake right here. I actually have 2 of these molecules. So I should have 8 carbon hydrogen bonds here. So, or sorry, 8 carbon hydrogen bonds attributing. Therefore, if I go back a little further, that actually accounts for 28 plus 8 is all 36. So I'm going to cancel all of those out. For my carbon hydrogen bonds, I should have, or sorry, for my carbon carbon bonds, I should have 2 of them. So going back and editing this, my final formula instead looks like this. 4 hydrogen carbon bonds minus 2 carbon carbon double bonds. So now I can plug in my values. 4 times 364 minus 2 times 614, which gets me a total value of delta H equals 228 kilojoules per mole. Finally, moving on to the last problem. Determine the enthalpy change for the reaction using the data provided in section 13 of the data booklet. So now we're going to do it using the enthalpy formulas, which is on your data booklet. In your data booklet, we know that delta H of formation is equal to the sum of the delta H of our products minus the sum of the delta H of our reactants. So when we do this, we find that delta HF just equals our products being this one down here and that is going to be negative 315, or sorry, 311.5 plus 52 times 2. So that 52 comes from ethene, C2H4. That's in our data booklet. We are going to subtract our negative 393.9. We get a total answer of 186 kilojoules per mole. All right. And with that, we have completed the entirety of the test. Hopefully this helps. Please review it as you need and have a good day.